morning and welcome again to Intro to Geology, and we're going to be working on Chapter 8 today on mass movement. This is a rather interesting topic because it really affects us on a daily basis. There's some unique stuff that we'll look at today. I'll be talking about some of the types of mass wasting. Up front, I'm going to show you a lot of pictures of examples. I'm sure you've seen some of these in the news. We'll talk about some of the reasons and forces behind mass wasting, and then I'll go off on a tangent like I often do, that things you don't find in a textbook, and show you some stuff that's happening around the country and the world, as well as right here close to home in Kansas, some types of mass movement you may not be aware of, and show you a little bit about what some of the things Fort Hays State's doing with this kind of stuff and research we're working on. So this is Chapter 8, and let's go ahead and get going on it. The very opening picture is a typical picture you see in the news about what happens when it rains too much out in California, and all of a sudden the slopes start coming down and you wind up seeing somebody's house or sliding down the hill. Well, that's what mass wasting is about. It's the idea that large masses of the surface of the earth are moving. They're kind of wasting away, kind of a form of erosion, I guess. They're moving downhill. Now, most of the types that we see and look at where it's moving down some slope like this. There's other kinds, though, that actually where the ground is very subtle in its movement, and it's more of a vertical drop. And I'll show you a really good example close to Hays, Kansas about that has been happening for quite some time. Here's one in Zion National Park. So as you look at these pictures, obviously something that disrupts our life, whether it be destruction of homes, in this case a road, and makes it difficult to get into a national park, and hopefully they're back on site fixing these things rather quickly. Here we have a road outside of Aspen, Colorado, and down there, kind of close to the green arrow, down towards the bottom, you can see that car that wasn't quite paying attention, I guess, and wound up down there as the highway disappeared. A lot of different reasons why these things slide downhill, and that's what we'll be looking at today. Here's one near Thistle, Utah, that half the mountainside slid down, covered a river. The river dammed up into a lake and flooded a small town, along with the railroad tunnel and a main highway to Salt Lake City in Utah. And so for a long time, probably about, I think it was 9 to 10 months before they could reroute the highway back on its track, the people living in Thistle had to drive many, many extra miles to get to work every day. It was extreme inconvenience to them. They got the tunnel back for the railroad, and the new highway was rebuilt on the bottom, and they eventually drained the lake out as well. But large amounts of debris and rock were moving downhill. The one on the left, you can see large boulders that have just basically fallen straight down. A rather scary possibility of a rock fall out there in Utah. Another large, massive hillslide came down in Montana back in the 50s. Again, covered up a river, dammed it up, and then a huge lake formed behind it, which they call Earthquake Lake, of all things. So what would be some of the reasons of why this kind of stuff happens? You know, everything we saw was pretty much a lot in mountainous terrain. Well, here's a spot kind of down in flat Florida, where the surface of the ground just caves downward, sinks completely in the ground, what we call sinkholes. You can see a variety of structures and cars that have been sinking, and sometimes these are very quick and very active. You can stand along the margins, you don't want to get too close, but you actually see this stuff just sinking right underground. So what are reasons behind that? This was in the news a lot last year, these big mudslides on the west coast of California near Conchita. In fact, there have been mudslides along this particular part of the coastline for the last, several hundreds of years. Yet people still, like living in this area, and they keep coming back, and then the slides occur and provides a danger. You see these older pictures here. There's one from 1995, then 10 years later, another one takes place. Certainly you wouldn't want to see something like that, especially if you're driving along a main highway. Huge boulder, and of course the engineers have to get in there, the highway people, and remove it. Get the road opened up again. Well, right here in Kansas we have a form of sinkholes as well. They're not your typical common sinkholes. you might think of associated with limestone terrain, where the limestone dissolves out and creates caves, and the surface will begin to sink in. This is similar, but it's different. This is near Hutchinson, Kansas. For those of you here in near Hutchinson probably are aware of what this is. I'll come back to that sinkhole and some of those things later on. Take a closer look at some of that stuff here in Kansas. And of course, these are not rocks, but certainly there's large masses of other debris. In this case, snow and ice come blowing down a hillside, and avalanches, and snow is just as important to investigate the reasons why, in terms of, what kind of snow is it, what's the crystalline structure, what can we do to block it, protect the highways and the homes, and a lot of jobs associated with avalanche research. As geologists, though, we're concerned about the rocks. A lot of students wind up with jobs with like KDOT, Kansas Department of Transportation, or the Colorado, or whatever state they're working for. And in the engineering aspect, they want to know why are the roads, why are the hillsides falling onto the highway? What are the features that are in the rocks that cause this? What do we do then about it? So kind of up front, we're going to talk about the kind of variables of the reasons why rocks do this and what happens to them. And then in the end of the class today, we'll get into things we do about it, the mitigation process. Because usually when things happen, there's always litigation, which is a legal aspect. Mitigation is something we do to fix things. Well, this is a geologic map of the United States. Now, all those pretty colors up there represent different types of rocks of different geologic ages. And I'm not going to go into the history of that right now, but if you look at it, there's a lot of diversity. And think about the rocks you've already learned about. Igneous rocks, metamorphic rocks, and sedimentary rocks. They're all different kinds of characters within each of those. Some rocks are extremely hard, very resistant, very strong, very durable, and others are weak and easily break down and easily fall apart and can move. So that's what the geologists look at as we try to understand what kind of fractures are in the rocks, how old are the fractures, how many, which way are those fractures oriented, and how does that affect, what part of the country are we in? Does it rain a lot? Is it dry? That has an effect on looking at how that rock moves. What's the potential for mass movement? Now here's this map. It's a landslide potential map. It's not a slumping map per se, but it's a type of map that shows where would be the more dangerous places to be for certain kinds of mass movement. Obviously in the Appalachians on the East Coast, in the Rocky Mountains, and kind of the West Central, and along the West Coast. And we think about the West Coast there in California and those mountain ranges. And of course in California there's a lot of earthquakes. And earthquakes, that vibration can help cause things to move, to trigger it, to upset the stability of those rocks. If you look at Kansas right there in the very middle, we have a little green patch kind of running through there. The kind of mass movement we have in Kansas is not super bad. It's not real dangerous. There's a few small little pockets, though, that can be. And we'll look at least one example of some of those in Kansas that can be kind of dangerous to our health. All right, so let's go through a little note-taking now in terms of what are some things that control or factors in terms of the stability of a slope. Obviously, the main force pulling on a massive rock is gravity. It wants to pull it downhill towards the center of the earth. As geologists, we want to know about composition and structure of slope materials. Composition, as I said, is the rock type. Igneous, sedimentary, or metamorphic. If it's within igneous, what kind of igneous rock? Is it granite? Is it basalt? If it's a sedimentary rock, is it a really well, hard, cemented sandstone, or is it kind of a crumbly shale? We'll see that different kinds of rocks are more prone to be unstable. That's composition. Structure is more related to things like which way are the layers in the foliation layers in metamorphic rocks, or the bedding layers in sedimentary rocks, which way are they oriented? Are they tilted towards the highway, or are they tilted back into the slope? That makes a difference. Are these rocks fractured? How many joints are fractures? Are they just full of them, or is there only a few? Because don't forget, those fractures allow what? Water to get into them. If the water freezes and expands, it pushes things apart, breaks them down quicker. So a lot of things can happen in terms of composition and structure. How much water is present in that rock system? The more water we'll see in the next slide, the worse things get. So I'll come back to that in just a bit, but the amount of water is a factor in terms of slope stability. Steepness generally is a factor in the sense that the steeper the slope, the more unstable the potential on that slope to fall down or slide or fall. If we say, well, okay, that means horizontal ground, nice flat ground's the safest. Not always. The picture in Florida with the cave and the sinkholes. The picture in Kansas where the ground just caves vertically downward. Other things come into play to cause even horizontal ground to be unstable. The presence or absence of vegetation. Usually the presence of vegetation is good. Usually soil will help hold the vegetation will help hold the soil together, hold the rocks together. Certainly root growth getting bigger is going to weaken a system, but we often see on construction sites we try to revegetate a surface so it doesn't erode real quickly and get back into the highway. So on the average, having vegetation there is better than not. All right, so that's kind of the setup. What's going to make it take off and move? What would be some good triggering mechanisms? Well, one thing is to overload a slope. There's lots of ways to overload a slope. You can build structures on it. You can bulldoze other material onto it and add more weight. And if that weight pushing downward, of course with the force of gravity, adds the extra little kind of shove to make things move, that'll do it. Another way to actually cause a slope to become overloaded is to undercut it. Go into a sloping hillside, cut a vertical wall into it, and then put a highway right there or build your house right there. I'll try to show you a picture of what undercut means in just a bit. Certainly if you cut way under and have an overhang, you've got something going to go straight down. You'd have to bolster that up, protect it somehow. Vibration. As I said, earthquakes can trigger things to begin to move. Just shake it enough, it'll actually weaken, and a lot of things can happen. Now, it doesn't have to be from natural earthquakes. This can be from daily traffic, heavy-duty trains and trucks close to certain slopes. That constant low vibration can do it. And certainly quarrying operations where they're detonating charges in mining. Okay? Always having that kind of energy to dissipate into the rock. And lastly, add water. Adding water does a lot of things. So I want to go through a list of things now about water. Obviously, adding water adds weight. That's overloading the system. And the presence of water, we already saw in the chapter on chemical and physical weathering, water can break things down. Chemical weathering, if you have water in the system and it freezes, it expands, that will weaken the rock, make it unstable. And of course, water also acts as a lubricant or a buoyant. And all of a sudden, things can begin to move. So overall, water's what? Water's not good. Water's bad as far as slope processes and stability are concerned. So remember that about water. Water is not good towards mass movement. Here we have a slope that's been, the vegetation or much of it's been destroyed by a fire. So whether this is by natural fires or by arson fire or even deforestation, remove the trees, that increases erosion. Therefore, it's going to speed up the process of mass movement. Again, whether it's natural or some anthropogenic type of activity. But fires and deforestation increases that capacity to weaken a slope. Interesting little kind of tidbit about the island of Madagascar, a little small continent off the east coast of Africa. There's this river system that flows through there, and there's some really good forests on Madagascar, or there were. They went in there because of the desire to have some very exotic woods and deforested that whole place. Left everything open to the rains, and tons and tons and tons of soil was being washed off the surface and removing mass material and shedding it down into the rivers. The picture on the left was taken in 1981, and the yellow line is kind of a reference line in all these pictures, a reference line of where the topography is. And the blue line up here, kind of or green, I guess, on the TV screen, is showing kind of where the front edge of this mass of new sand and new gravel is being migrated out in this delta. Usually deltas take a long, long time geologically to advance outward, thousands of years sometimes. We'll take a look at this change. Look where the blue line is in the middle 4 years later, where the sandbars are migrating as this tremendous amount of sludge has come off the surface of the land. And eventually, 12 years later, it's moved way out, all because of deforestation, removal of those trees. All right, we're going to kind of simplify the types of mass movement today. I want to kind of go through a list of 4 styles or types, the way in which these rocks and other debris move downhill. And one way is simply fall, and this usually refers to where it falls straight down through the air, lands at the bottom of a cliff somewhere and piles up as rubble. So those are fall types. Things can slide. And that depends upon, of course, the structure and the steepness of the slope of how they slide and how we might, we can talk about a mud slide, we can talk about a rock slide. Things can get even more wet, more aqueous, almost like a really thick, muddy river flowing. So we use the term a style of flow because it behaves more like a liquid than it does a kind of a solid mass of rock. So falls, slides, flows, and then something called slumps. And slump is related to slides in a way, and even some kinds of flows, but there's a special case with the slump, and I'll show you a picture. It has to do with the way in which the ground is fractured when this actually takes place. Instead of being planar, it'll be more of a curviplanar, a curved surface. And again, I'll show you a picture of what that looks like. So falls, slides, flows, and slumps. And there are a few other styles that I'll look at that are very specific cases. But these are the major ones we try to categorize things into. Here's an example of kind of a landslide that is a result of undercutting a slope. On the left, you can see where they cut into the hillside. They flattened an area to put a house in. And then, according to the cartoon here, they put a cheap wall up. They put this thin concrete retaining wall up instead of maybe putting steel pilings into the ground and much thicker concrete wall to hold the weight of that upper zone back. Because if that gets wet, it's already over-steepened in that respect. And you can see in the other cartoon here what happens. This is kind of what happens in many, many cases. It takes a lot of money to really shore up a hillside better, and even then sometimes Mother Nature is just stronger than what we can throw at it. Up in Alaska, 1964, they decided to build a housing development out on kind of an old, what was a sandy area that underneath it was an old swamp. A lot of wet, muddy clays, little silt pockets, but very full of water. All right? And of course the sand and gravel on top is very porous, and water would soak right through that. So well, let's build our houses on top of that. In this case, well, along comes this earthquake that just vibrates and shook the ground. And it kind of began to liquefy some of this mud and silt and clay beneath there, and all these slumping pockets took place, and it took all the houses with it. So they decided to move everything. Everybody had to leave. Every house was pretty much destroyed. All right, rock falls, just a few examples. Again, the rocks would just simply fall straight down and then, of course, pile up in some slope debris material like this, a talus pile. So real photo on the left and kind of a cartoon over on the right. I won't go off on any of the physics of that, but you know, stuff's, when it hits the slope, can begin to bounce and roll as well, like the boulder we saw out there in that California highway as well. So it depends on the size and shapes of these. Slides we try to think of as being more where the rocks are not going straight down or bouncing down per se. They're more sliding in mass, usually along some kind of a planar feature like we would see up here in the top left in the cartoon, where the layers of rock are kind of steeply tilted towards the valley. Although the rocks that make up the Sierra Nevadas in California, where we find Yosemite National Park, all the rocks out there are pretty much homogeneous large plutons of granite. But they're highly fractured, but they also have some other fractures caused by unloading. Remember when we discussed unloading, creating these big curved sheets of rock? Water can easily get in there. Well, this is what's been happening in a lot of areas of the park that we're just not around all the time, but large rock slides and rock falls take place. And unfortunately, 10 years ago, there were some campers down underneath that who didn't make it. Kind of a little disaster, but the rocks broke loose and large boulders came down on the other side. And that is the debris pile that's left over. But you can see on the lower left the sheeting structure, the top up here on a little map of where it broke loose, and then kind of a little, that talus pile or debris that covered a hiking trail, some of the climbing areas on that slope, but mass wasting, a type of rock slides. Here's a close-up of that Montana rock slide I mentioned, damming up the river. And of course, it created quite a mess. Now, as we begin to add a little more water and add a little more vegetation, especially the water, we kind of say that this moving mass behaves more like a liquid, so we can classify it as a flow, probably moves a little faster. And also, if it has more trees and vegetation, we can say it's kind of classified as a debris flow as opposed to a mud flow. If it's all mud and moves fast, we simply call it a mud flow. If it's more vegetation, it's called a debris flow. Like I said, I gave you the four main categories, but we can go off on lots of different possibilities with each if we wanted to. Like this, if it's mostly soil, you could classify it as an earth flow, or if you wanted to, a mud flow in that case. More mud, I guess. There's a subtle difference between earth flow and mud flow, in my opinion, where they do classify. And I think maybe there's a little more water and finer muds with a mud flow as opposed to an earth flow. Maybe like back in this, you might have more sand, more silt sides. Nevertheless, it's still behaving like a liquid and moving downhill and, of course, causing problems. Now, this one is totally different. It was not on the list. It's referred to as creep. Now, when you look at this cartoon example of this, what you see are a whole bunch of structures, whether they're natural or man-made. We see the highway, a bit of curb, a fence, telephone or power lines tilted over, trees bent over, a house bent over, the rock layers in the upper cross-section kind of tilting and bending downhill. Creep is a very special kind of mass movement. It's extremely slow. It's so slow that trees can continue to grow, and yet their tree trunks will show that curved or bent nature because of that movement. Trees always want to grow straight up towards the sunlight. But if their root system is sliding downhill, it wants to tip the tree over. But the tree wants to grow straight up. Here's kind of a picture of the fence falling over. You could say, well, it's a cruddy fence. Or usually what happens is that post is either, moving downhill with the upper part of the earth. Soil creep, even though it's not super dynamic looking, never makes the news per se, it's the one that costs us the most money because it's always going on everywhere. It's not so climate or geographically specific as in some cases, or special needs to vibrate it and so on. The surface of the earth is always slowly breaking down and sliding a little bit. Whether it's your foundation to your house or a highway or a fence or whatever, you have to fix it. This is the one that costs the most money to repair. So don't forget that about the most money. Here's what happens to trees where you can say, well, you can see that surface and see how they're bent like that. The ground is wanting to tilt that system over as it slides downhill, but the tree wants to grow vertically straight up. Good evidence of surface creep. All right, now slump, I told you, is a special case where the way in which the rocks move downhill, they move on kind of a curved surface. A curviplanar detachment that takes place. It slips along that. In the top left, it's in rocks. And in the bottom, it's more of a soil type of thing. We see a lot of that stuff that you see on the bottom out here and a lot of the shales. You can see some of these near Lake Wilson area, that more hilly area on Interstate 70, or drive some of the back roads. You see a lot of that where it begins to detach, and it's just a slow kind of downhill movement, but it's a curved breakage of mass. And of course, the ground is rather disrupted. Shale zones will have a lot of this happening out here in Kansas. A lot of the back roads that are built on shale have to be fixed because of slumping underneath the road. I take our senior geology students out north of Hayes to a place along the Saline River where there's the most dynamic kind of structure, as I call it, and large-scale, thick layers of rock that the students can map so they can be prepared to go out to Colorado and Utah in the summertime to complete a different course. And out along the river, there are some of the most unique structures that are slumping. I want you to kind of look at the cartoon on the right-hand side. All along the Saline River, there's an escarpment that's held up by a resistant limestone. These little brick patterns in the top cartoon, or top segment of the cartoon, are Fort Hays limestone. And underneath that are little layers of Codell sandstone, and then some huge crumbly shale, of the Blue Hill Shale underneath it. Now these limestones are resistant out here because it's dry, but they're fractured. There's huge joints or fractures that are vertical, and so there's a weight of these masses pushing downward. And they push out onto, or down onto those shales, and the shales then bulge out towards the valley. And you can see in the second middle picture that they're kind of getting wrinkly and crumbled as that slowly begins to slide down along the joint. And eventually it ends up, like in the bottom of the picture, where it's tilted or curved. Now when you take a look at these real pictures, the one where the big yellow arrow is right here, that's the Fort Hays, and then below it is the Blue Hill Shale with Codell right underneath that. Take a look at this rock layer. This is the Fort Hays up here. Underneath it's the Codell. Same in the bottom picture. This is the Fort Hays right here. Just to the right of it, it's the Codell sandstone, the Blue Hill Shale. These things have slid down or on a curviplanar structure and slumped such that they're now steeply dipping. This rock layer here is dipping this way into the hill, so it came down and slid out away from it. Whereas this one, the escarpment's to the left, and this thing curved way down and got real tilted like the lower picture in the cartoon right here. So some of the more dramatic types of mass movement we can find right here in Kansas. I want to jump to some ground now that we may have mentioned early on, but permanently frozen ground. In North America, more so in the purple area, and especially the orange area up there, I think it's red on the screen, up in the Yukon territories, this area of the ground is permanently frozen. Whether it's here or whether it's in Siberia, okay, in this part of Russia, that upper ground, the groundwater is frozen solid, sometimes 100 feet or more. When it warms up, things can happen. In the summer seasons, when that ground gets the solar radiation, starts to warm up, or we build a highway through it, or we construct a house on top of it, and increase that solar radiation for increasing the heat, that stuff melts. And what we get is a very special kind of mass movement you need to remember. It's just like creep in the sense that it's very, very slow. And it's referred to as solifluction. Solifluction takes place in the polar regions of the world, where we have this slow downhill movement because of the permafrost melting in the summer seasons. Now you still may have frozen ground underneath that, but the upper few inches or a few feet slowly slides down the hill, kind of like molasses. And if you've built on it, it's going to take the structures with it. Solifluction is in the Arctic regions more so, permafrost regions. Here's a real photograph in the Brooks Range, on the north side of the Brooks Range in Alaska. You can see that kind of slumping or that slow kind of lobate movement of that material downhill. You can go to the University of Alaska, Fairbanks campus, and get a degree in studying how to build things so that doesn't have melting permafrost destroy it, how to kind of mitigate solifluction. You can see those houses up there in the top right inset. We've learned to make things a lot better up there now, how to dissipate the heat. Don't let the heat get into the ground to melt this. Nature's going to do it anyway. You don't want to speed it up. So if you build a highway or you expose that dark soil under there, that's going to absorb heat. Here's kind of what it looks like. That's just solid. You can go up there with a rock hammer and pound on it. It's like hitting solid ice. You can hike around in some of those places, and that ice is lurking all around underneath the soil, that permafrost stuff. A close-up of this white ice here right in the middle, you can see that the crystals of ice are real long and skinny. They nickname it up there needle ice because it looks like long sewing needles of some sort. But that stuff expands and contracts and expands and contracts, and of course if it melts, things slide downhill. Way up in the Yukon, there's the Inuvik village, Inuvik. There's a few smaller outliers even further north up there. Inuvialuit, you can see just off the Beaufort Sea. They take advantage of the permafrost. They don't have a lot of money. And there's not a lot of major roads up there. The only way you get in there is flying. So sometimes they would take and simply dig a hole underground and go down that permanently frozen ground, and this becomes their freezer. Just take their food down there. Let's hope it doesn't get too much in terms of global warming. They're going to have some spoiled food. Probably the biggest contention's been our oil pipeline up in Alaska from the North Slope, where we bring a lot of crude oil down to southern Alaska, ship it out to be processed. In this picture you can see a zigzaggy kind of structure on the left-hand side and a more straight, sinuous road, so to speak, on the right-hand side. I'm standing on the road, the main highway there, and that's what they call the haul road that goes up to Prudhoe Bay. And that's the pipeline on the left. Well, when they constructed this thing, they had to really take care about permafrost and having solifluction problems and so forth. There's natural earthquakes in Alaska. And if you look at this, you can see these big fins sticking off the top of this structure. Those fins are there to dissipate heat. Now, what kind of heat are we talking about? The heat is from the hot oil pumping through that line. There's a smaller tube running through that pipeline. Then there's a big, thick insulation layer around that. Then the outer coating of this that you see on the outside with the straps. And that oil is hot. And that heat by conduction is going to move outward and get into these support structures. And if that got hot and went down into the ground, it would melt the permafrost. So they said, we got to keep everything cool on the outside, keep it hot on the inside, but cool on the outside so it doesn't melt the ground. So they dug these huge holes, about 3 foot in diameter, put these hollow stainless steel pipes in there, put these cooling towers on the top. If you take a close look at a motorcycle engine and take a look at the cooling fins on a motorcycle, they're to dissipate the heat. Well, these things are the same way, and like I said, that job you can get in Alaska, what's the best way to build these for different kinds of structures? I remember driving outside of Fairbanks in this open field just full of all these kind of looks, to me at first I thought it was a junkyard. It turned out it's an experimental station for all kinds of shapes and styles of fins to dissipate heat for whatever we have. So even wilder on this pipeline, down below it there's a little section right here that there's rubber shocks, and then that kind of supports that. Then this little kind of support steel structure here that can slide sideways, so if there's horizontal ground movement, that pipe will not break. That whole thing will shift back and forth, but hopefully not move enough to break. And so far, it's never happened. So they put a lot of thought and engineering into this thing for whether it's earthquakes or whether it's the permafrost to not have the structure break down. All right, I'm going to shift to a special kind of movement. Now, remember, all the ones we looked at pretty much now were kind of things sliding down a hill or falling down on some form of slump or slide or fall or flow. There's a special category called subsidence. Now, it's pronounced subsidence or subsidence. Either way is fine with me. But close to home, if you've ridden on Interstate 70, you've probably seen this in the past. And it's just east of Hays, Kansas, some miles, and I'm going to focus on more of these types of subsidence here after I make a list. Subsidence is defined as the vertical downward drop of the land. The vertical downward drop of the land. Now that can be fast or it can be slow. In the case of the sinkholes on I-70, they're slow, fortunately. The picture in the bottom right-hand corner of this slide right now, this is in northeastern Ellis County, not too far from the interstate, north of Walker. And that hole, which was about 105 feet wide and 110 feet deep, opened up overnight. Now imagine that kind of hole opening up overnight on the interstate. That would be kind of frightening to have happen. That was a form of subsidence for a reason. Now, what can cause a vertical downward drop of the land? Fast or slow? I'm going to go through a list of some things right now. Number one is something called hydrocompaction. I think you know what compaction means. Hydro means water. Now, I want you to think about going out and doing construction. In this construction site, you're ripping up the land, you're tearing it up, you're fluffing up everything by bulldozing stuff around. Now what you're supposed to do when you're done and you're going to start putting a foundation or something in, you want to go in there and pound that ground back down flat. That doesn't always happen. Doesn't always happen. Sometimes a few pockets are still kind of fluffed up and the little grains of clay are stacked like a deck of cards. You make a little house card or, type of thing, and you pop the bottom one off and the whole thing collapses, compacts downward. Well, if you got it ground like that and water percolates into that fluffed up ground, the water, hydro, causes everything to collapse. And all of a sudden you've got no support underneath the edge of your foundation, your sidewalk, a certain entrance to part of Tamanic Hall at one time when they were first building a structure back in the mid-90s, or a canal that takes water out of the Colorado River for miles and miles and miles and takes it over to Southern California. The Great American Canal is a big concrete structure. They were too much in a hurry in a few places, and hydrocompaction, just things disappeared and there was no support and the concrete cracked, and where'd the water go? Into the desert. Strange things happen like that. Hydrocompaction. Another thing is through fluid removal. Deep underground, if you've got water, that water's in the pore space, the more water that's there, the higher the pore pressure of that water. You pull the water out, the pore pressure drops. And all the little grains want to compact and settle closer together. You can take places like Long Beach, California, Galveston, Texas. All the removal of petroleum caused it to sink downward. It took a long time, but there are places along those coastlines, like in Long Beach, you can go to restaurants and hospitals and police departments and libraries and whatever, and you're 20 feet below sea level because of all the removal of petroleum in the subsurface. So fluid removal has an effect on causing the ground to move downward. Now solutioning, you notice I have a star on it. Solutioning goes back to chemical weathering. Remember that? Talked about how water can dissolve things like calcite real easy because it's got carbonic acid and other organic acids in it. And so if you've got limestone terrains that are made up of the mineral calcite, that groundwater will start totally dissolving and everything's gone. You get a cave. All right? You have no rock support. All of a sudden the ground above it starts to just collapse and sink inward. That's a sinkhole. When we get into the chapter on groundwater, I'll show you some other examples of sinkhole situations, but you're dissolving that out. You're solutioning it out. Well, below Kansas, below out here, there's a rock layer down there called the Hutchinson Salt. Now, salt can dissolve real easily. And I'll be coming to pictures of that in just a bit. And once you dissolve that rock, the support's gone and things can cave downward, a form of subsidence. Probably the most rare and weirder type is called organic shrinkage. I know at times in the past, through human intervention, we've gone out and we've drained water out of swamps to create land, to create real estate on purpose, so we can put in housing developments and so on. In Michigan, in the lower peninsula of Michigan, I forget the 40s or 50s, they put some housing developments in, cheap housing, and they had drained out these swamps. Now today we can't drain swamps. Why? The Wetlands Act. It's illegal to drain swamps. You can't get rid of that. But in the past we could, and so they'd drain the swamps, go in, put some sand down, and build a house. Well, what was happening, by draining a swamp, you lower the water table. When you lower the water table, oxygen can get to the organics, and that causes them to dissolve, causing the rock, the organic layer, to shrink downward. And lo and behold, all those old housing foundations did what? They got cracked. Everybody got moved out, and they didn't go back in again. Organic shrinkage, another weird type. And of course, the biggest little underground activities is mining. Tunneling underground for coal or salt or gold or whatever it is. And if you don't have rock go back into and be a support there, when we're mining, we want to leave pillars for support while we're still working. But the other way is let it cave in eventually. When that happens, what happens to the surface of the ground above it? It drops downward. A form of subsidence. Here's a cross-section from west to east across these sinkholes. One's called the Crawford Sink. I'm going to go back to the slide here. This is the sinkhole in the top right-hand corner. That's called the Crawford Sink. That's often had water in it. Doesn't now. It's been dried up lately with a drought. But this is an older picture of the highway where it was curved downward. And there was a sinkhole. I'll get to the reason why it happened in just a bit. The sinkhole in the bottom right, same reason why it happened, is referred to as either the Nielsen Sink or the Chrysler Sink hole. Now, along the interstate, though, this is kind of a drawing of showing us a profile of how the ground is dropped. Now, the vertical exaggeration is very high to amplify our ability to read the diagram. But what you need to remember is that Interstate 70 right there is sinking 5 to 6 inches a year. And since the last time they went in to try to fix it, it has sunk 19 feet. When I first came out to Hays, Kansas, the road wasn't that curved down. In the 25 years I was here, it had gone down and gone down and gone down. It was sunk when I got here, but it was not like it was by the year 2004, 2005 when they went in to fix it. And I'll show you what they did to fix it. And if you've ridden on the highway in the last several years, you've seen it. We certainly wanted to build a highway system, an interstate system, to provide jobs and move food goods and so on, and move people. Here's a picture of a sinkhole back in the 1950s, when they were planning to build the interstate system in the United States. It was President Eisenhower who wanted, help get the interstate system going, a Kansan. So they said, well, about 1,000 feet down in this oil field, this active oil field, there's a big salt layer down there. And we think maybe the ground here might be down and subsided because of this oil field related activity. And so maybe we shouldn't build it through this oil field. Well, they did anyway. They wanted to get it done. They got it through the Gorham oil field. And so about 1,000 feet down, is this salt deposit called the Hutchinson Salt. And of course, the geologists, the oil people, drilled 4,000 feet down below to get into the oil producing horizons. Once in a while they drill a well and they don't get any oil. It's a dry hole. So what they say, let's case it off, shut it off. Don't need it. But if that whole casing isn't done properly and it rusts out, things can happen. And that's exactly what happened. Some of this casing eroded away because it was done poorly along some of these wells, and these porous sandstones in the subsurface were now open. These porous sandstones that had water in it. And surrounding this well, there's a vertical line running through here, surrounding this well were other wells just pumping and pumping and pumping and pumping water. or excuse me, petroleum. Okay, pumping petroleum. Well, since they were pumping petroleum all around it, instead of the water going straight downward and away from the salt, what did the water do? It came up and came through the salt. Okay? And so what that did, I got that backwards, excuse me. The water was sucked downward through the salt layers, and when it went through the salt, what did it do? It dissolved it out. Normally water you'd think would rise back up in the well by natural hydraulic pressure. Okay? But since they were pumping oil on the sides away from this, all right, that meant, if I can try to do this with a screen here, they were pumping out here, that means the water was going to be pulled this way towards the side. So these sandstones up in here, the water in them, got sucked down through the salt and out that way because of the hydrostatic head that got built up, got pumping outside. So they told them they had to stop pumping that way. And they've done that, but nevertheless, what happened is all this salt dissolved out and this thing slowly slid down and collapsed. Now in the case of the one in northeast Ellis County, bam, it happened overnight. Here's kind of a picture in the 1960s. They were trying to, they had elevated the highway back up, nice and horizontal, and they were in there in that sinkhole trying to fill it with concrete. Fill a big open hole down there with concrete and salt. Well, they pumped everything, the whole state's budget practically for the highway, for the emergency fund, not the highway whole thing, but the emergency fund, went into the hole. And 3 months later, that concrete was being dissolved by the salt. We didn't have additives that we knew about back then, so it kept going. And it's still going on, still happening. So in 2004, April 24th, I had the luxury of being invited out to mile marker 178. They put a whole bunch of material underneath the overpass here, and they set charges on this, and they kaboom. Except they made a mistake. For some reason, the wiring wasn't good here, and this still stayed. So they had to finally go and blow it up when the next blast, it finally went. And then, since that time, they started building the highway back up. And now when you drive over there, you hardly notice it was there. The highway doesn't dip down. The overpass is gone, that landmark you might have been used to. And they've been going on and fixing it now. Now, more recently, Fort Hays State, our department, got a 5-year grant to measure the subsidence. We go out there 2 to 3 times a year. We started our first survey last November. We're going out again in April this year and see how much it's gone down. See if it went down, 2-3 inches. And they'll go out there every year. We get to pay our students money. They get to learn how to do surveying. They get to learn to do a variety of things with this. Kind of interesting topic. But at a more high-tech end of it, we're doing something else with this little acronym right here. See this SRI? Mentioned that earlier, I believe, and with volcanoes. Satellite Radar Interferometry. Dr. Heinrichs wrote a grant. He's our chair in our department to the European Space Agency, ESA. And we'll be purchasing satellite radar imaging to have students be involved with looking at this imagery over the years too, and see if we can tell what's going on with how the ground's, maybe on a more accurate level or further away from the interstate. So we've got two different combined kind of grants working on the same project, and we'll see how it goes. Mining, as I said, you just dig out underground and things are going to collapse if you don't fill them in. So mining-induced types of subsidence. Here's structures in Virginia and other parts of the country where, you got the structure of house in the bottom right, the foundation breaking. Here we've got the railroad system totally dropped down. You certainly don't want to take a train on that. Somebody's front yard just totally sinks in. Here's a huge one. A lot of subsidence. Remember what this might be? Here's some wet, sandy, clay, mud oozing up in somebody's basement. Liquefaction. Nicknamed sand boils or clay boils, where if you got this wetted sand and you vibrate it and shake it, that pore pressure might squirt out of the ground and squeeze up. That removes material from underneath so the ground can collapse, but it also can squeeze into places that could be dangerous, like up there in the top left in that railroad system. If enough sand comes out and covers a track, it could derail a train. So liquefaction, where wet sands or clays are, become liquefied when you shake them, not stirred. Pretty James Bond fans in the room. Sand boils are a nickname we kind of imply, kind of a crass name that's in the literature, but it's out there. If you're moving to San Francisco area, a lot of land development, I'd look at this map very closely that's available through the city. A liquefaction susceptibility area where they would bulldoze rock and debris into a small swamp way back when. They can't do it anymore, but they created lots of real estate. So underneath it, you've got the potential like what happened in Alaska, up in Anchorage with that earthquake. Another kind of mass movement material, a huge kind of rocky mud flow of volcanic stuff. Remember the term lahar? We looked at lahars in the chapter on volcanoes. So lahar would be an example of a mass movement. All right, so that's a lot of the stuff. What do we do about it? What are some things we can end up with here today to talk about mitigating it? Mitigation means some form of prevention to try to either stop it or slow it down. Stop it or slow it down. Litigation with an L, of course, is a lawsuit. And a lot of times these two things go hand in hand sometimes. Well, one way is, I don't know if you ever had a broken bone and they put pins in your leg to kind of support it while the bone grows back. Well, imagine real large pins. We call them rock bolts. In the top left-hand picture, you can barely make them out, but in the bottom two pictures, the bottom half of the screen, you can see the end of these two large bolts. They drill a hole 20, 30, 40, 50 feet back underground, put a large steel pipe in there, pound it in, and put a big nut on the end. And so they're kind of trying to join and stitch layers of rock underground together to keep this outermost layer from falling down. And you can see in the top left-hand picture that overhang right where the word rock bolts are. That's going to come down sometime. This is along Interstate or Highway 50, I think in Colorado, just west of Canyon City. Or, like in the top right-hand picture, we could try to put some kind of thick, heavy-duty steel netting up there. A little rock breaks loose, falls, hits behind the net, and dribbles down to the bottom. Just to keep it off the road. Keep it from hitting us as we drive along or walk along. Here's kind of a cartoon of the rock bolt idea. Create that support in there. Here's a test area that there's this graduate student you can just barely make out in the top middle where the arrow's pointing to. Hand pounded tons of little nails in to put this netting in there and they were going to compare the amount of movement on a slope where they didn't put the net versus putting a net to say, would this kind of net work? Because we're talking a lot of money when it takes to mitigate these things, to protect us. That's state tax dollars spent on that. And so this is kind of a research area. Here's this undercutting. You can decide to put rock bolts up here in the top right-hand part, or you can put a big retaining wall right here, or you can remove the whole thing. Depends on what budget you have. It boils down usually to money. What have you got? What kind of stuff can you put in there to prevent erosion? Here's a little kind of cul-de-sac in California, the end of the road that's completely surrounded by steep slopes all around on the sides. Somebody spent a lot of money to terrace that, to put those drain water pipes. Why did they put the pipes in there? To get the water out of the slope, because what? Water's bad. You don't want water in there. You want to have a lot of drain pipes in there to get that water out. Plant vegetation. You can see that their attempt to plant vegetation is slowly kind of picking up on that canvas or tarp they've put on there. So terracing, anything you can get to put together to kind of stabilize the slope. Here's something that's really used a lot. Shotcrete, special kind of concrete you spray onto a surface. In this case, they're spraying it with over metal rebar on that slope. A lot of times they just go out and spray it right on the outcrop, right on the shale. Like in the bottom right-hand inset picture, they just went out there and sprayed that stuff on that slope. It looks like real rock, but it's not. It's a form of concrete, and since they're shooting it out of this kind of hose, they call it shotcrete. I think that's a trade name. About a year ago, I was heading out west, and I was north of Phoenix. Sun's going down. I thought, oh, the colors get so pretty this time of day. Look at this pretty red outcrop. And I kept looking at it and looking. I said, you know, that doesn't look real to me. Closer I got, so I pulled off. Sure enough, it wasn't. It's shotcrete. But they wanted to make their shotcrete look real, look natural. They went out there and they hand-carved little joint pictures. They spray painted it with paint. Take a look at the very top edge right up in here. You can see that shotcrete. You can see the gray concrete, and it's real thin. That's eroding off right here. They spent a lot of money to make that look natural. They wanted it aesthetically pleasing. I mean, a lot of this stuff, some people think, hey, this is ugly. We want it nicer looking. Well, this is the best I've seen so far. It's pretty cool. But Costs money. So whether it's retaining walls like we've got up there on the top left with that steel rebar you can add in there, to having a kind of a roof over the highway as you drive through, a rock shed or some kind of a tunnel through the mountain. A really strange one is referred to as a gabion. They'll take a kind of a thick wire mesh and fill it with rocks and make big cubes, and then they pile these cubes up like Tinker Toys in a way, little building blocks. And of course, that's certainly cheaper than some other things, but it's whatever you can do. From, like I said, tunnels and rock sheds to gabions is one thing. You might want to even put big steel pilings behind your retaining wall. That's a pretty steep wall. It's a pretty steep slope here in the bottom right-hand corner behind that. You certainly want to shore that up. You wouldn't just put concrete up there. That wouldn't hold. You've got to have some kind of a backing with some strong steel supports behind that. And certainly a lot of drain holes. See those little holes in there? Those are all drain holes to get water out of that slope. The springs, you'll see it frozen up. You see the icicles hanging them on in the wintertime. Another thing to do is kind of like inject something underground to harden it up. I've seen around here where they'll inject things around foundations of houses, and then that stuff stiffens up underground, solidifies, and then prevents water from seeping into your basement. There's a whole group of these different kinds of things. We call them grouts. You drill a hole or you inject this stuff underground, it hardens up, and kind of as a way to stabilize the ground. Like I said, there's lots of mitigating things we can try to do. There'll be new things we hopefully will invent in terms of mitigation to prevent litigation. Because things do happen in terms of mass movement. So something that affects our everyday lives. This chapter is kind of interesting stuff. And next time you drive by the interstate area on 70 and take a look at that old sinkhole there, kind of think about what happened about 1,000 feet below us on the highway there. So that'll be it for today, and we'll see you next time.